Okay, so homework 7 is here. Homework 8 is, I think, probably posted. I can't really remember, but it will be, and it's due a week from today. It will involve the box counting dimension. You're going to make fractals in MATLAB, pretty pictures. And there's code already for you on the site that computes the box counting dimension of them, and you're just going to like press return, download, press return, make pictures, and tell me what you think about them. Again, the concept behind this idea is lots of things we observe in the world are rough and don't resolve when you zoom in on the boundary. They are going to have a dimension that's not an integer. That's confusing. We're talking about it. How do we measure dimension? Well, we make these boxes one way. We make boxes, and we count the number of boxes that have a piece of the stuff in them. And then we cut the boxes in half, and we cut the boxes in half again, and we cut the boxes. And each time that, there's lots more boxes, but not all of the new boxes are going to have pieces of the set in them. So as the box size shrinks, the number of boxes that have pieces of set in them goes up. The reciprocal of the box size also goes up. So the rate at which the box size reciprocal goes up, the rate at which the number of boxes that have stuff in them goes up, that goes up too. And these things, we're measuring the exponents of these things and their ratio. That's the dimension of our object, at least in this box counting thing. Today we'll talk about a different way to measure dimension that will be probably a little more confusing, harder to draw, but it's good for data. Cool. So for the non-map, we've kind of finished last time with we finished last time by I guess I just told you what I think the slope was for the box counting dimension for this set, with doing another like 3 or 4 of these resolutions, at which point the picture is just all black, so that's not good. And we got an answer for the non-map. I think its dimension was something like 1.27. This was the BCD of the non-map. And there's some numerical stuff going on, as I said. So, if our orbit is length 1,000,000, and then eventually I've made my box sizes small enough that 1,000,000 boxes have stuff in them, there's no way for me to like cut the box size in half again and get more boxes with stuff, because there's only 1,000,000 points. That's how long my orbit was. So it becomes difficult to resolve more and more digits of these things, as just like in the past we've seen. And okay, I also mentioned that in higher dimensions, this is 2-dimensional data. These points, each of these is an XY pair. But lots of the systems we study are much higher dimensional than that, and it becomes really hard to count the boxes in higher dimensions because there's so many more boxes. Let me see if I can explain why that is. So if we take an interval and we do the box cutting thing, we take an interval, we cut it in half, 2 boxes. Cut those in half. Each of those boxes, we get 4 boxes. And we cut those in half, we get 8 boxes. The powers of 2 are going up one at a time. If we're in 2 dimensions, we have a grid, and I cut the grid's size in half, I get 4 times as many boxes. If we're in 3 dimensions and I have a cube, and I cut the cube sides in half 3 ways, I now have 8 little cubes, which is from 1. I started with 1. If I'm in 3 dimensions and I have a cube, and then I cut each, do you see how I'm going to end up with 8 little cubes? Yeah, each with side length a half. So that's 2 to the 3. I get 8 times as many. And then if I did it again, I get another 8 times as many. I had 64. And if my dimension's 4 instead of 3, just put a 4-dimensional unit cube in your head and start slicing that thing up. It goes up by a power of 2 to the 4 every slice. So this gets problematic in terms of the size of, or the number of boxes to pay attention to as the dimension goes up. I'm talking like, okay, 10 dimensions, box size of length 1/100th. There are 10 to the 20 boxes, for example. And lots of the data we care about is much higher dimensional than 10. So the box counting dimension thing, cool. We can draw it. You're going to work on it in your homework. But it's not super practical for a lot of the data we have. So we'll talk about another method today to quantify dimension. And then ultimately, we're going to end up using this Lyapunov exponent to quantify dimension. That's coming later. That'll be the thing we end up using the most. All right, so just one last thing about measure and these weird sets we're talking about. Here's a theorem. We're going to let A be a bounded subset of Rm with BCD of A being this dimension D, and we'll say that that dimension D is smaller than M, the space that it lives in. So the Anon map, this is in R2. You know, coordinate pairs X and Y required to identify points in the Anon map. So it's R2. The function is in R2. And the dimension we got, D, when we measured it, was smaller than 2. I'm trying to understand what that means. Okay. So if this is true, we're going to let A be a bounded subset of Rm. Here, you know, the attractor for the Anon map is a subset of R2. With the box counter dimension D smaller than M, 1.27 smaller than 2. Then A is a measure 0 set. Doesn't take up any space. Measure is this concept of space, so in R2 it would be area. The Anon map doesn't take up any area, because its dimension is smaller than 2. If its dimension was 2, okay, then it would have some stuff to it. So there's some concepts about measure. We'll just write down a few. A point has measure 0. For example, in R, also in R2 and 3, but a point, if I think about a point, that doesn't take up any space, right? Lots of weird consequences of that idea. We've talked about some of them. It doesn't take up any space. A line has measure 0 in R2. So, you know, I got a long interval, has length in R, but if I put it in R2, it's not taking up any of the space. I can make R2 by stacking an uncountably infinite collection of these. This is one way to go to higher dimensions above 3, is to think about stacking representative members of a lower dimension. A plane has measure 0 in R3. So R2, you know, that's a plane. I can turn it around, but it doesn't take up any volume. These are just some examples that we know already to get us familiar with what's happening here. A plane does have measure in R2, right? There's some area. Yeah?
Is there a way for a point not to have measure 0? It's kind of off topic.
Yeah. Well, let's think about what's the middle third scanner set. What's weird about that? Well, it's uncountable. Bunch of points. So many points. Can't even list them. And it's measure 0. But if I think about the irrationals between 0 and 1, they do have measure. They're measure 1.
But just
a point, a single point.
Yeah. Is there like a...
Can I put a little ball around it that has width and say the only thing in that ball is that point? No. You want a point to have space. It feels wrong. It's like you're demoting it, but it's not enough stuff. Other questions? This is a theorem. We're going to prove it using our BCD that we just talked about, this box counting dimension. All right, so the box counting dimension said that my D, this BCD, is the limit as epsilon goes to 0 of the natural log number of boxes of size epsilon in the numerator and the size of the box goes in the denominator in its reciprocal. Because as epsilon gets smaller, 1 over epsilon gets bigger, so you got the numerator and the denominator fighting. That's our box counting dimension. And we're going to work with this until we end up, showing that, if this is true, we have a measure 0 set. Yeah, Rohit.
the dimension is between n and n minus 1, okay, does that imply that we have fractals right away?
Good question. Yeah, so Rohit's question is, if the dimension D of a set A is between M and M minus 1, like it is for the Hanon map here, then we have a fractal. Yes. Yeah. And in fact, we'll be able to have fractals, this is weird, but we'll be able to have fractals whose dimension is an integer also. We'll see things like that. In fact, on your next homework, you're going to see an example of that. But okay. So I'm going to mess around with this. Things that I can do. I can pull a negative out, right? This is ln of e to the, or epsilon to the minus 1. And the log rule says I can bring that minus 1 out in front. So let me do that. This is the limit. Epsilon goes to 0 of ln of n. I'm going to drop the epsilon because we know what n is. Divided by minus ln of epsilon. Epsilon to the minus 1. Log rule says I can bring that minus 1 down in front. And I know from my theorem, the proposition here that m minus d is a positive number. So if I take m and I subtract this thing right here, I should get something bigger than 0, according to what we've written down. Okay, so let's write that down. So I've got limit, epsilon goes to 0. I'm going to stuff the m in. M doesn't care about epsilon. It's just whatever integer was the size of my space to begin with. I've got an m ln of epsilon plus ln of n divided by n ln of epsilon. And this thing has to be positive. So I've stuffed my m in. This minus sign is that one right there. M has an ln of epsilon attached to it, so I can get it into the fraction. So, if I think just about this is m. And then this piece is negative d. This is negative d. So this thing is supposed to be positive. What's happening? M is just an integer. Epsilon is getting smaller. N is getting bigger. All right, I'm supposed to get a positive number back. And log rules say I can, if I have two logs, that I'm adding up, I can stuff them together. So this is going to imply then that the limit as epsilon goes to 0 of, I'm going to make my numerator a little simpler, ln of epsilon to the m times n divided by ln of epsilon. This is positive. So this m, I can go bring it up here as the power of epsilon inside the log. And then I have one log plus another, and I can stuff those together if I multiply the two arguments of the log. Playing with exponents. That's what we're doing here. All right, so this is supposed to be positive. I don't know that I'm any closer yet. I must be. I'm writing things down. What's happening to the numerator, or what's happening to this in the limit? The denominator, what's it doing? Maybe, it's always helpful. Let's draw the log function on the board. This is ln. That's always good. What happens to the denominator as epsilon goes to 0? Cool. So the argument of the log, epsilon is going to 0. It's getting closer and closer here, which means the function is going to minus infinity. All right, so this denominator is going to minus infinity. The whole thing is supposed to be positive. What does that mean? The top is going to minus infinity faster. Okay, that's kind of a head scratcher. Well, one nice thing, if epsilon is going to 0, then epsilon to the m, where m is an integer, that should go to 0 faster, don't you think? All right. Let's write some things down. So since the limit as epsilon goes to 0 of this denominator, ln of epsilon, is minus infinity, according to our log function, we know that the numerator, limit epsilon goes to 0 of ln epsilon to the m times n, this is also minus infinity. It has to be. If it were something else, then we would be getting 0 as an answer. If it was some number, if it was converging on a number, for example. Okay. So going back to my log function, what does that mean about this argument on the inside? What does it mean about epsilon to the m times n if the log is going to minus infinity? This in here has to approach 0. That's right. Yeah. Because in order for the log to go to minus infinity, the only way that can happen is if this thing approaches 0. So that implies, very good, Scott, that limit as epsilon goes to 0 of epsilon to the m times n. That limit is 0. Good. Okay. Maybe I should go back to my thinking about this. Like, what are these things again? What is epsilon to the m? What if m were 2? What if I were a two-dimensional thing? What is epsilon squared? It's the area of our box. Nice. So we got a box here. Here's epsilon. Here's epsilon. Epsilon squared is the box area. Okay, we got our box area. What's n? Sweet. Number of boxes. So I got number of boxes times the area. What's that? It's the area of whatever the heck I started with, right? It's the area of A. Yeah? I got my epsilon. It's raised to the, however big my dimension is of my space that I'm in to start with. So maybe it's 3, epsilon. In this case, it would be 3. M is 3. So I get the area of one of these cubes. And then n is the number of those cubes required to count the set. Okay. Cool. And that is headed to 0. All right, I'm going to read my definition of measure. What do we say a set with measure 0 was? Does anybody remember? Definition of measure 0. True. There was the word covered was in there. So this says that there are epsilon boxes. This is the volume or area of them. This is how many I have. That cover my set A and whose total volume, length, area, total is headed to 0. And that's the definition of measure 0. We can write that down. There exist boxes, epsilon boxes, covering A, whose total volume feels like the right word here. Total volume, epsilon to the m times n. That's the volume of an individual box. That's how many I have. Can be made as small as we want. There exist epsilon boxes, which just means that the boxes all have side length epsilon. We could use rectangles. We could use banana-shaped things, but this is easier to talk about. So as we're doing this, we're zooming in. The fact that the box counting dimension of the non-map is 1.27 means that, we don't ever get to some resolution at which, like we keep getting more and more boxes contained inside an area. That's never what happens. There's always a thin strip of boxes next to each other, and if we carve those boxes up by making them smaller by a factor of 2 or a billion, there's still just that small thin area. There's just more of those near each other. That continues to happen forever. And that's why we have something that isn't just one. It would be one if there was just, like if I took my marker down and I would get dimension 1 doing this, because eventually those boxes would all shrink, and then eventually they're just all, I'm getting the exact number of them, and it would look like one-dimensional. If I look down, all these boxes are all lined up next to each other. That's not what happens. We zoom in and actually, it looks like I got a strip of boxes, but go in a factor of 100, and all of a sudden there's 25 strips of boxes, but no continuous area. I think we have some of these pictures here. Yeah, okay, here we go. Here's the non-map. Here it is. Zoom in on a little bit. This is what it looks like. Like if we zoom in on this bit right here. This is what it looks like. And then if you pick one of these little pieces, like this one, and zoom in on it, like put a little box here, zoom in on it, there it is. And there's more stuff. And we pick this little box and zoom in on it. So the boxes that I'm showing you, these are the boxes whose area is epsilon squared. And we're zooming in, but we're not ever at the resolution at which there's just a strip of them. There's always lots of strips of them. So it's more than one-dimensional. But it's not two-dimensional because they don't contain any, it's never a point where I was like, oh, I got this whole region full of boxes. All right, questions about this? Yeah.
If it's 1.27 dimensional,
Yes.
I'm still having a hard time wrapping my head around it.
Okay. Great. The question is like, well, it's still weird to me that, it's not 1 or 2. There's something weird going on. Yeah. So if it were 1, we would zoom in on this and we would see a line. And we'd have a row of boxes, which when we cut them in half would still be just a row of boxes. It'd be twice as many. But I cut them in half. And then if I cut them in half again, there'd be 4 times as many. But I had cut it in by 4. And so the fact that those numbers are going up together, 4 and 4, 8 and 8, that scaling is one-dimensional thing. It's a line. That's not what's happening. As I zoom in on, one of these things, it looks like I got a strip of boxes lined up. I don't. I get a lot of strips of boxes. And then if I pick one of those and I zoom in on it, it becomes a lot. But it's never the case that as I zoom in, I get a whole region where I need boxes, and I make them all finer, and I still need all of these boxes, and I make them all finer, and I still need all these boxes, which would be the case if I did this with a square, the interior of a square, or the interior of a circle or something. And that would be two-dimensional. It's neither of those things. It's less than the 2D, and it's more than the 1D because of this continued infinite resolution business. Okay, yeah.
So if we had something similar, but it turned out that it was like 1.8.
Yes.
Would we just see more? Is that like more density?
How much space does it take up if its dimension is 1.8?
Nothing.
No more space than this one does. Yeah.
So how? What's the difference? Like why is 1.27?
Does this look?
Different than 1.8?
Does this look to you to be as complex a structure as we could generate zooming in on a curve of any variety? Not really, right? I mean, it's like they're all straight lines. So in that sense, it's more like a line than it is like some set that takes up area. There'll be fractals whose dimension, let's say, it's like 1.97. You start zooming, there's going to be, it's taking up a lot of space. Like there are these sort of space-filling curves that you can draw that, where you can dial the dimension to be as close to 2 as you want. What's the game? Is it like the worm game where it gets longer and longer and you got to turn it around so it doesn't snake? Is it snake? Am I saying the right words? I stopped playing at Super Mario Brothers back in 1987, so I need updates on it. Although that one was older. Yeah. Rohit, yeah.
From what you just said, so let's say, you earlier you mentioned that with all these fractals, it can be applied on like CGI and like making graphics that looks real.
Yeah.
So if we dial the fractals up from 1.27 to 1.8, would that make the graphic looks more real?
So the question is, if we had a mechanism to dial this for a particular type of fractal, and we will, where we can kind of pick our algorithm that draws a picture to make it as dense as you'd like, would it look more real? Was your question? Well, it depends on what the object in the world that we're interested in, what its dimension is. So, for example, if you think about turbulent, waves on the surface of the ocean, they don't take up three-dimensional space, but they're very different than, just a nice smooth curve, which would be a two-dimensional surface. So I might say, if you were looking to create like realistic, mountain range or skin of a Tyrannosaurus Rex, or that you might dial it up away from 2 and closer to 3. Does that make sense? Okay. Other questions? Andy.
So I see how we come up with this stuff analytically.
Okay.
Clearly it works.
The box counting thing.
Yeah,
Okay.
clearly it works with math.
Yes.
But like in a natural system, you can only go so far before you hit molecules and quarks or whatever.
Yeah,
there's
that's
a
right.
limit. I mean, you talk about like the English coastline.
Yep.
Eventually, you are going to get a line.
Yep.
Right? Like, so does this stuff apply to things that we think of, that we talk about as being fractal in nature?
Yeah.
Does it actually apply in reality?
It depends on your definition of apply. So you understood the example that I told you about measuring the coastline of England.
Right.
No one in England cares about the difference between those measurements, beyond a certain resolution.
Right.
Yeah. So, where it really matters is in technology that uses fractals as the building blocks of, whatever descriptive thing is going to happen. So in the case of CGI, do people enjoy the movie better if the skin of the Tyrannosaurus Rex and the surface of the waves look realistic? Of course they do. Like, that's why they pay so much money. It's the super fast computers. And so it matters there. It matters in modeling things like time series that are super rough, like financial time series, objects like the clouds I mentioned on the first day that, which are difficult for computers to resolve because they have fractal boundaries. But in practice, every one of the things that I'm talking about in reality, has some width of length scales for which it's a fractal, above and below which it makes no sense to talk about it that way. It's only mathematically that we have these, we can do the limit as epsilon goes to 0. In practice, it's like, we have these 3 orders of magnitude of space of spatial scales where this, there's this cool thing going on.
It's fractal for all practical.
Yeah, that's right. Yeah.
If it was more like an object less than the curve,
Yeah.
Would its dimension be like 2 point something? Like somewhere between 2 and 3 dimensions, or like even higher than that? Or is it always going to be between 1 and 2?
Good. Yeah, it depends. So the question is, what are some other objects that have shapes that are fractal objects whose shapes are bigger, whose dimensions aren't just between 1 and 2. Basically, that's what you're asking. It's like, well, let's see some different things. So I think I have a thing here. So this is a Wikipedia page that's linked on the website for the class with just lots of examples of what the fractal dimension of this set is. And some of which you're going to play around with and do the calculation yourselves. It says Hausdorff dimension. There are lots of ways to calculate this thing we're talking about. I'm going to end up talking to you probably about 3 total, box counting being the first one, because it's sort of the easiest to understand, but not great in higher dimensions, as I discussed. So we have these sets that are where the boundary is interesting. the Julius set, this is a picture when, the C value is I, which was one of the ones you made a plot for in homework 7. So its fractal dimension, if you measured it, was 1.2. It's it's one of these connected curves. You pick up your pen, or you can draw a line, a pencil, but it doesn't contain any area, like the filled-in Julius sets do for other values of I. Okay, this will just continue. So these are continuing to get more interesting. You change the value of C to something else, and the Julius set will continue. Its dimension will continuously change. It has to. Remember, the Julius set J when C was 0 is just the unit circle. So if you think about just that curve, its dimension is 1, or that circle itself, with area, its dimension is 2. Lots of ways to make these things. We're moving towards 2 dimensions. A Kita map, that's fun. I think we're going to play around with that one later in the semester. So here, things are starting to fill out, right? There's more stuff here. You can see finer resolution. The boundary of the Mandelbrot set, dimension 2. That's weird, right? So a 2-dimensional thing, that's got to take up space. Well, this better be curving around quite a bit then if it's going to take up enough space to be R2. If you contain the interior of it, like the M that's white in this picture on the inside, of course it's 2 because there's volume, and that makes sense. These are space-filling curves. There are ways to draw a single, an infinite length curve like the snake that I was talking about, but that take up space. And then, objects we'll spend the last week or so of class. I haven't mentioned this. This is going to be cool. We're going to do an experiment at the end of class, like a physical experiment. I bought a bunch of subwoofers from Best Buy, hook them up to an amplifier, and make fluids do really weird things. That's happening. We're also going to talk about an experiment that related to weather prediction that builds this Lorentz attractor thing. So we get this shape in 2 dimensions that or this is in R3. It spends most of its time down in sort of a flat 2D plane, but then occasionally shoots out. This process does, and when it does, it's only there for a little while and comes back in. And so this is basically 2-dimensional, but there's some extra stuff for every time it kicks out into this 3rd dimension orthogonal to that plane. All right, Apollonian sphere packing. My gosh, lots of cool things. Sponges, Hilbert curves, Mandelbulb, to be confirmed, conjectured. Here's your opportunity to get on Wikipedia. Oh, my word. So people do all kinds of crazy things. The people will, crochet these things because crochet has very nice topological properties. It's like, the kale. You can get lots of space from the edges because the edge grows more than the... Yeah?
Does the boundary of the Mandelbrot set too, because on its boundary it just has an infinite amount of things coming off of it, and that's why it's taking up space?
There'd be a lot of ways to do it where it wouldn't be too, though. So there's got to be something special about it. But yes, you're getting at it, the idea. Yeah?
Are the fractals limited to 3 dimensions because we're looking at a 3-dimensional space?
Okay, great question. Are the fractals limited to 3 dimensions because we live in a 3-dimensional space? All right, I was doing this with the cube. So if I want to make R4, people think about this different ways. You can think about time, you can think about a cube sitting there. Time is ticking by, that's a 4th dimension. Or you could just have like an infinite collection of tubes. Like R3, I can make it by taking R2 and stacking up all of these planes together, and I get R3. I can make R4 by taking R3. It's not a cube, right? It's everything spatial, and then just stacking a bunch of those together. Which time is that's why people talk about time as a natural way to. We could make 3.7 dimensional fractals, but you couldn't put them on Wikipedia in a picture. You could project them into a plane, a 2D plane. You could project them into a 3-dimensional space, but you wouldn't see all of it.
I feel like that feels like a tan exactly because it would be stretched out over time. So it's like a 3.
Yes. I don't want you to think about fractals in time because your head's going to hurt, but spatial. Think of this 4th dimension as spatial, then what you said is true. Yeah. time will not be able to be carved up infinitely, potentially. Open question. Other questions? Okay, I have a couple other things to say. What else do I want to say? Okay. I guess I have a couple videos that I wanted to show you. All right, this is on the board. Might as well talk about it. How many of you have heard of the traveling salesman problem? Okay. So it's this is a problem in computer science and math that people have been talking about for a long time, trying to find good algorithms for how to solve that. Basically, is the concept is somebody's got to visit a lot of places, and you want to find the best way to do it, and that's if there are lots of places to visit, like thousands of cities that a salesman has to visit, the order in which they do so, there's lots of ways to do that. The number of combinations of visits. And so if you pick one and then decide, well, if I want to try another one, is it better than this one? You can compare their distances and decide, oh, this other one's better than that one. But there's just so many to compare. It's one of these problems that's very computationally difficult. And people have been trying to figure out ways to do it, swapping random visits, and then, provided that the new visit, the new itinerary is better than the old one when you keep it, but occasionally, like every so often, you want to take this visit structure that's bad, that's worse than the one that you're at, and use that one because otherwise you get stuck in these local minima, and you don't ever find one of the best solutions. So that's a really hard problem for computer scientists. Apparently, slime molds don't have any problem with this at all. This is an experiment that people did not so long ago. Some scientists in Japan, and they put down some food sources and they laid them out, kind of mimicking in a little petri dish, mimicking the major cities in Japan, including Tokyo. So and then what they did is just put a little piece of slime mold down, and the slime molds figured out the best ways to get from one city to another to get their nutrients flowing around. They did it really quickly, like in 24 hours. This isn't a traveling salesman problem, but there are lots of examples in nature where having this type of, and this is if you look at transportation grids and solutions to traveling, they have these sort of fractal properties that nature takes advantage of in certain situations. This is one of them, to do things that are really quite remarkable. And there's a whole cottage industry now of scientists trying to figure out, applied mathematicians like myself, trying to figure out how to leverage solutions to engineering problems that biology has solved through evolution over many years. And this being sort of like a fun example of that. But I have a couple other examples that I wanted to show you. One is of like, so here's a leaf. I think this is, I must tell me this is a ginkgo leaf. So here's a ginkgo leaf, and some horrible person has hole punched the ginkgo leaf to see what happens to nutrients when the nutrients get sent in. And here is an example, delivery structure that, unlike the slime mold, does not have fractal properties. So these are one-dimensional curves that the pipes are, feeding the goods out to the edge of the leaf. And so there's a whole part that dies because of the hole punch. There's a whole section of it it's not robust to that perturbation, this design. Failure. Okay, so that's the ginkgo leaf. And then, so here's another. This is a lemon leaf, I think. Yeah, lemon. So you're going to see something different happen here. So somebody has hole punched the main vein in the lemon leaf, but it's got this fractal structure to its veins, where it's more resilient, it's more robust to that catastrophe, and it survives just fine, despite a major artery being punctured. So this is a more robust design, and you'd think that lots of the things we see in nature would exhibit stuff like this, otherwise they wouldn't be here. So if you look at your circulature, the system of how the blood moves around your body and your brain, how neurons are connected, there's lots of examples where evolution has produced systems that exhibit this robustness to catastrophe. You hear about people having a brain injury or like they're missing some part of their brain when they're born, and yet other parts that don't typically do stuff are, they take up the slack. That's another example of this sort of thing. So there's lots of examples in nature where fractal, just, in this case, it's like the pipes that get the food from one place to another, is a very advantageous delivery mechanism. There's a whole course about this in the fall, if you're interested, Math 300, about this kind of idea. Complex systems. Yes. You had a question, Scott.
Oh, no. My question was, do I have time for that?
Yeah, you probably do. Yeah, you should all sign up for Math 300. Other questions? I see one person's very excited to... Okay, I will be, if you don't see homework 8, it's coming. Turn in homework 7 on your way out if you haven't already.